All right, good afternoon. All right, let's get started. Okay, so last time we talked about determining the deflection of a beam using superposition, and then combined with using the basic solutions from the menu or from the appendix tables, right? So later on, in the real world, when you do some analysis, all this table you can find from a handbook or textbook, right? So you can use it to solve your problem. So we went through two examples in detail. One is a cantilever beam. Another one was a simple beam, right? So at the end of the class, I kind of draw a few different possible questions that are, ask you to look at it. I don't know if anyone try any of these solutions. No? You're not doing homework, right? So maybe today we'll quickly go over one more example, or you feel you are okay with this part already, or we can move on to use time for other things. Move on? Okay. All right. So then we'll just move on to talk about new things. And then we have actually more challenging stuff coming up. All right. So we'll spend more time there. Okay. So the next thing I want to cover is about straightness of a beam. Okay. So we talked about straightness before. When you stretch a bar, right, you have an elongation, then you have the straightness, right? And when you say twist a shaft, okay, let's use this page here. We can quickly review what we learned. Okay. So when you stretch a bar, okay, how do you determine the straightness in this bar? Anyone remember the equation? Energy half, right? There is 1/2 something. P delta, always the force times the displacement, right? Because why there is a half there? Because if you plot the P over delta, it's like a spring, right? So it's a linear spring. And the area that the work done is this area, the triangle. So you have a half there. And the work is converted to the energy. Then when it's bouncing back, the energy transfer to work. Right? So that's why you have a half there. Okay, now what about if you have a shaft and you apply a torque, T here. So what's the straightness? Anyone remember? Right, half of the T theta, right? Sometimes you call, I think we use phi or theta. We use phi, right? Okay, but that doesn't matter what letter you use. It's mean the same thing. Okay, so it's pretty easy to remember. They're all half, right? The load times the angle, or movement time angle, or the force times the distance. So it's basically load times the displacement, right? Okay, now in this chapter we want to talk about for the beam, right? When you're bending a beam, okay, so let's say you apply moment here, M. You say, why you have to apply a pair moment? Can you just do this way, apply a moment, M here? This to the same thing, right? Because the reaction moment will equal to M anyway. So this either this one. Okay, when you bending a beam, how much energy you store there? That's the question we try to answer. Okay, can you all guess what it will be look like? The U will equal to 1/2 of M times, what's the displacement when you're bending it? Angle. So it will be angle theta, right? And you're absolutely correct. So we'll be looking the same. So you can see the pattern there. So it's actually help you memorize it. You don't even need a formula sheet, right? So you can memorize it. Okay. All right. So that's the conclusion. Okay. Now let's just look a little bit detail why this is correct, kind of like a mathematical proof, right? If you're not interested, you can take a quick nap, but I think it will be helpful. We look through. Oh, okay. So, all right. So here is a detailed derivation. Okay. When you have a beam, you're bending, you basically generate deformation, right? So we know this equation. That's how the curvature relate to the bending moment, right? But if you look at it, actually, if you look at the theta, right, the angle you turn is actually given by this equation, right? You all accept this equation. Because the dx, we always know the arc length, right, is the radius times that small angle. So dx equals rho times d theta. That's why you have this equation. Okay. Once you know this one, then your d theta will equal to that because you plug this equation in there. Okay. So therefore, for that small element dx there, you're going to do this much work, or you store this much energy. The du, this, right? The local energy stored there is the m times that small angle change. Now, how can you get the energy of the whole beam? You add all them together, right? Adding together, that means integral. So you just put the integral there, and you get the whole thing. Okay. So therefore, right, you get this equation. So that's the derivation process. And this one, okay, that's a general equation. So whenever we talk about moment, how much energy is stored there, that's the general equation. Okay. For one special situation, if you have a m equals to constant, and we call that pure bending, right? You just have a m everywhere, the same m. And then m is constant, so you can throw it out. So once you throw it out, you'll get this one. So for a constant moment, yes, that's the equation. But in general, even the moment is changing everywhere, then for each local site, location, right, local element, you're going to store this much energy, the one inside. And so the total you just do the integral. So whenever you know the mx, and then you use this integral, you get the energy. So it's pretty straightforward. And again, why we need to know the energy? What's the use of this strain energy? It's related to potential, right? It's the energy stored in the beam. And you actually can use this equation later on to do analysis. For example, for numerical simulation, numerical analysis, finite element, you're going to use some energy. One approach is using the energy equation to get the deformation. So what needed there? Okay, so for this particular course right now, we're not going to use this energy not much. But remember, we did show an example back in chapter 2. We can use energy to determine the displacement. Same thing can apply here, but we don't have the time. We're not going to go to detail. How to use this equation to determine the deflection of the beam. Okay, so but just quickly, anyone can think, how can we use this equation to determine the deflection? For example, if you have this beam, okay, let me go to the next page. If you have this beam, okay, applying load P here, how can I determine the deflection, the maximum deflection, say this point? You can use the energy approach. Because the P, right, travel distance delta. And so you have the work done will be P times this delta maximum and a half. That's the work done. And that's supposed to equal to the energy stored in this beam. Right? So you find out M, then use this, you can determine the delta. So really quickly you can do it. Right? Okay, so that's basically the application. You can use the energy to determine the deformation. Okay, any question about the strain function? Strain energy? All right, is that clear? Okay, if this part is clear, this is mainly the concept, right? If this is clear, okay, I think we can move on to look at another stuff. All right, let me see if we keep this one. and then shrink it. Okay, so I want to talk about something what we call indeterminate beams. Okay, so we already went through indeterminate problems. If you have a bar, right, multiple restriction, then you can have indeterminate bar. Have a shaft, you have, let's say, between two walls, when you twist it, that's become indeterminate problem. Okay, now for the beam, we'll have the same situation again. Okay, so first question will be, what's an indeterminate beam? All right, so let's say we'll go through one example. Let's say I have this beam. Okay, make it easier. Say I just apply a load P here, just one load. Okay, now for this beam, is determinate or indeterminate? Determinate. Okay, how can you know so quickly it's determinate? We used it before, right? We saw it before. Okay, what's indeterminate? That is when you have lots of restrictions, right? Reaction, force, or movement. And when you try to write the equation of equilibrium, you cannot find out the reaction by using equation of equilibrium alone, right? Now, in this case, you're going to have a R, let's say RA, and another MR here, right? So you have two unknowns, two restrictions or reactions. Okay, now, how many equations do you have here? You have sigma Fy equals 0. That's one equation. So from here, you get Ra equals P. Right? Now, what's the second equation? Moment to point A equals 0, or to point B equals 0. Right? So from there, you can find the reaction moment Mr. So we can find all the reactions. So therefore, it's determinate. Right? Because you are so familiar with it, without writing all this equation, you can see, oh, that's it, determinate. Okay. But this beam, oftentimes, if you use this beam, maybe if you apply load here, this point can deform a lot, right? So often in engineering application, we want to make sure you have enough restriction so they don't deform too much. Like in the body, right? Since in the body, there are multiple points that are supporting it, actual support, because you don't want to make it easily deform. So there are actual restrictions to it. If, for example, one bone, right? Because one bone here, you have many muscle attached to it. So therefore, if I move it, that's one movement here. Okay, all the muscle applying force to it. So let's say 5 muscle here. 5 muscle applying forces. How many equations you can write? Only 2, 3 equations. Right? Of course, if you say 3D, yes, there will be more. Right? 3 sigma fx equals 0, that's 3 equations. Sigma f equals 0, that's 3 equations. I mean 3D, right? And then the moment equals 0, that's another 3 equations. So you can have a total of 6. Right? But you have 5 muscles. How many loads there? The force, each one has a sigma f is a fx, fy, fz. So 3 times 5, you have 15 unknowns. So definitely that will be indeterminate structure. So human body, many engineering application structure, they're all indeterminate because that's more stable, more reliable. Right? So therefore, you know how to solve indeterminate problem is actually very important. Okay, now back to this beam. Okay, so to make it strong, maybe I can provide another support here. Right? This beam looks like stronger because there's additional support there. So you can apply more load P there, it won't just deform too much. Okay, now is this determinate or indeterminate? Okay, maybe it's still determinate. Okay, let's find out. So what do you apply here? What's the reaction here? You're going to have a RB here, right? Okay, now what's your equation of equilibrium? You still have 2 equations because we're talking about 2D, right? Okay, sigma Fy equals 0. So you're going to have Ra plus Rb equals to P. That's 1. Okay, what's the second equation? Still sigma Ma equals 0, let's say, right? So point A is here. Okay, so you're going to have a negative Mr and then minus P times this, let's call this distance A here, right? Or half L, right? And then you have plus RB times L. That's supposed to be 0. Right? Okay, now how many unknowns? 3. How many equations? 2. So indeterminate. Okay, so therefore a quick rule, okay, quick judgment is we know what's the determinant beam, right? Simple beam, cantilever beam. What else? Overhanging beam, right? We talk about 3 type of basic beams. That's all determinant. Okay, if you have that, if you any of the 3 type of beam, if you add additional support restriction, or you add 2 more additional support, then it's all become what? Indeterminate, right? Like we show here. Initially a cantilever beam, determinate. Now you add 1, so it's indeterminate. Now what if you add another one here? Another support. Determinate or indeterminate? Definitely indeterminate, because you add 1, it's already indeterminate, right? 3 unknown. Now you add another one, have 4 unknowns, and you have 2 equations. So therefore, it's high level of indeterminate. And we actually call this degree of indeterminacy. So you have 2 unknowns, so the degree of indeterminacy will be 2. If you have 1 extra unknown, that will be degree of indeterminacy will be 1. Right? Imagine you can have many things here. Then you can have 5 degree of indeterminacy, right? Or 4 or 6. And so that's actually happening in the real world structure. Okay, now what if I have a beam like this? Applying load here, or maybe another load here. It doesn't matter how many load here, right? Okay, this one determinate or indeterminate? It's indeterminate. The reason is, okay, you're going to have a RA, RB, MA, MB. How many unknowns? How many? 4 unknowns. How many equations do you have? 2. So what's the degree of indeterminacy? 2, right? Because you have 2 actual unknowns there. All right. Okay. So next slide, I have a summary. Okay. So the type of indeterminate beam, the most common one we see. Okay. You can have one end fix. So fix pin. That's one, right? Or fix. That's another one. Or you can have multiple support, like this last one, continuous beam, right? You can even have more. Say you have more, this is very long beam, like a bridge. You have many support there. Long bridge, there are many support, right? So that's an indeterminate structure. Right. So that's the common type of indeterminate problem. So later on, when you see this, you immediately should know, okay, this is indeterminate beam. And so therefore, okay, how to solve it? How can we solve this indeterminate beam, or indeterminate problem? What we used to use? The fat.com, right? And that's still applying here. Okay, but there is a variation. So we'll go over how can you use the fat.com to solve an indeterminate beam. And there are mainly 2 approaches you can use. I don't think we have time to cover all 2, but we'll go over at least 1 approach. All right. Okay, so we talk about the degree of the indeterminacy. All right. So, okay, here is another concept. Okay, when you solve the indeterminate beam, the way to solve it is you remove the redundant restriction, treat it as an unknown force or unknown load, and then you solve the equation based on this as a determinate structure. For example, it's shown here, right? If you have this beam at the top, that's the indeterminate we just said, right? So the degree of indeterminacy is 1. So therefore, we just need to remove 1 additional load. Then it becomes a determinate structure. Okay, actually, there are multiple ways you can do that. For example, on the left, it's showing remove this load, remove this restriction. So you replace it with a reaction force, let's say called RB here. You say, I don't know RB. Yes, we don't know, but it's a load, right? So it's equivalent. The beam here is equivalent to somehow you have a cantilever beam with a load P there and the RB there. Of course, you cannot randomly apply any RB there. It must be some RB there. The correct RB will make it this one back equal to the top one. Right? So you can remove one additional restriction, and what we call redundant restriction, and then you can get a determinate structure. Okay. Then you can actually continue because this one is a determinate structure. Then you can move on to solve it. Right? And then there will be compatibility that give you an additional equation you can solve for the actual reaction. Because remember, compatibility is how the thing deform, how they related, right? And that'll give you additional equation, and you help you solve it. Okay, so that's one way you can remove the redundant. Another way is, okay, well, I can do this way. So I can change this beam, original, the top one, okay, to a simple beam. Because I can say, oh, I have a simple beam, then there is a reaction, say, call this one MR, or MA, actually, call here, right? If the MA somehow happen to be correct, and then this beam will be back there. So there are multiple ways, always multiple ways you can remove the redundant restriction and replace with the force or moment. But there's multiple ways. Some are easier than the other. In some cases, for example, here, actually these two are equivalent. They're about the same level of difficulty. Right? But for some are different. Let me see if I have the next example here. Okay, so next example is you can remove this one. We know the 2 degree of indeterminacy, right? So you can remove one the restriction, and then it become a cantilever beam. So basically, you're going to have one reaction and another reaction. That's all I know yet. Okay, we'll talk about how to find it next. But first, let's just remove it. Okay, or you can change to this one. Then you have to add what? You add this MA, right, and MB. So you can basically remove the redundant, whichever you think can treat as a redundant reaction, remove it, the restriction, and change with the force or movement accordingly. And then you have a determinate structure. Okay, determinate structure, we know how to deal with it, right? Okay, let's say if we look at this one, okay, the one on the left. This is determinate structure. How do you solve for the deflection, everything? You can use superposition, right? Or you can search the table, find the answer, combine with the superposition, and solve for it. Right? Or another way, you can say, if you know like this one, another way is you can just write the equation for the bending and solve for it. Okay. So let's go through this the second one first. Basically, how can we use the equation? Let's say for determined beam, we know we can use this equation, right? For example, or you can use the EI V4 prime equals Q, and you can solve it. So you can solve the equation, find the answer. I can tell you this will be a harder way, but I want to show one example to illustrate how we can use this. Then we'll more focus on use superposition, use the table, and to solve it. Right? So next time we'll talk about that approach. And that's a more, maybe a little bit easier approach. Okay, so I think here is the example we want to go over. Okay, so here is a beam. Okay, we cannot call it a cantilever beam anymore, right? It's not a cantilever because there's additional support there. So it's a fixed pin to end there. Okay, first, is this determinate or indeterminate? Indeterminate, because we are actually already covered. Now, what's the difference? The difference is the load is different. Previous example, you have a country force. This is a distributed load there, right? As I mentioned earlier, again and again, the load doesn't depend on, the load doesn't decide whether the structure is determinate or indeterminate. It's the restrictions, the boundary condition that determine, right? Okay, so this is indeterminate, right? So we can verify that by the equation of equilibrium, as you can see here. right? Sigma Fy equals 0, sigma m equals 0. So you have 3 unknowns and 2 equations. So you cannot solve it. All right. But based on this equation of equilibrium, we can get these 2 equations there. That's just the relation between all the reactions. Right? Although we cannot determine the number, but we know they're related this way by the 2 equations. All right. Now, how can we solve this equation? Okay. The way to solve it, we will remove the redundant restriction and then change it to a determinate structure. Then we solve it. Okay. So as we said, you can have multiple ways you can remove the redundant restriction. Okay. Here I'm showing one way is I remove the moment, the restriction to the angle rotation at the point A. And then, because I remove that restriction, so I have to put a MA there. So there must be a load there. And then because I remove this moment restriction, now it becomes a simple beam. So the structure of that indeterminate structure, now I reduce it. The word is reduce it to a determinate structure. That's a simple beam. Right? Of course, you can also reduce it to a cantilever beam. Right? That's another alternative approach. Okay, let's say we use this approach, reduce it to a simple beam. Now, for this simple beam, can we solve for the deflection using this equation, moment equation? Yes, we did that 2 lectures ago, or 3 lectures ago, right? Okay, so we start here equals that. So we find the moment. Is this the correct moment expression? Must be, right? Put it there. Right? So basically you can write, remember you can find your own node. If there is a distributed load, right, a simple beam, the moment at the initial location will be like that. If you're not sure, we can quickly draw the VM diagram. Okay, what's the VM diagram? V, you jump up, right? Then gradually go down, and then coming up. That's the shear force diagram, right? Okay, what about movement? You jump first, jumping down, right? MA is pointing this way. So you're jumping down, right? And then you accumulate positive area. So we'll be going up, right? And max point must be here. So you're going up here and then maybe going down here. So that will be, depending on the value, relative value, maybe it will be here. Right? Depending on the relative value, but it will be a parabolic equation. So that's this equation here. All right. So now we have the moment equation. So we can do integration twice and find the deflection V, and that is this equation. All right. Okay. Now we find the solution, but we have 2 integral constants. And besides that, we don't know MA yet. MA is another unknown, right? Because I can remove it, but I just label as MA, but I don't know the value. So basically, we still have 3 unknowns. Now, how can we determine the 3 unknowns here? How do you determine this 2 unknown? Boundary conditions, right? So we should do the same. Boundary condition. So that's a boundary condition here. V equals 0, V prime equals 0. Right? So that's the boundary condition we have. Use this 2, you can determine 2 constants. Okay, now we still don't know MA. How can I find out MA? Remember, this is what? The original question is an indeterminate question. We reduce the structure to a determinate structure. So we can use the equation, we came to this stage. Now, what indeterminate question or problems, okay, what's the additional thing you can use to help you add the equation? The compatibility, right? Okay, so when this beam deform, this beam, we look at it here. Okay, how can this beam compatible to this beam? I mean, the deformation pattern match this one. How can we match that? you need an additional equation, right? That match it. So how can this, let me change the question this way. Okay, how can this beam deform the same way as this beam? What's the condition that makes this beam the same as the other beam? How are they different when they deform if you compare these two beams? Okay, this beam, when they deform, what's the deflection here? 0. What's the deflection here? 0. Okay, now this beam, what's the deflection here? 0. What's the deflection here? So this is the same. Okay, now look at this beam. Okay, what's the rotation angle here? Can be any value depending on the MA, right? Now what's the rotation here? 0. Now how can you make these two beams match each other? Make that point equal 0, right? So if I can somehow find that I'm trying different MA, okay, somehow I apply this MA here, oh, this rotation angle equals 0, then what do you say? This MA must be the same as the MA here, because otherwise it will deform differently. So that's the compatibility. So I can make this reduced structure become compatible to your old structure, the indeterminate structure, by making the deformation, this boundary, the same as the other one, right? So that's a compatibility. Or in other words, the compatibility here is basically a boundary condition. So you have some additional boundary requirement, make this reduced beam back to the indeterminate beam, right? So with that, actually we have this equation here. So we have 3 equations, right? So the V at x equals 0 equals 0, x equals L equals 0, and then the prime equals 0 as well. So if we want to see, okay, among these 3 boundary conditions, which one is the compatibility? It's this one, the third one. So that's a compatibility. So you can hardly actually totally distinguish them, right? Because they all like boundary conditions. But that's the one link the old beam to the new beam. I mean the reduced beam to the original indeterminate beam. Right. So basically the key now, actually maybe a little bit easier now, is whenever we talk about you need additional compatibility equation, you just go look at the boundary, right? How the boundary moves can match the original problem. Then that's the one. Right. Okay, so for this, we already have it here. So you have this 3 equation. Now can we plug this 3 equation back to here? Or actually apply this equation to this boundary? Can you determine the C1, C2, and the MA? Yes, mathematically yes, right? You have 3 unknown, 3 equations. Okay, so we can determine. All right. Let me see if I have the final. Actually, I don't have the final there. Okay, so therefore your homework, based on this, determine the final solution, then compare to the textbook. I think this compare to their solution. See if you get the correct one. Okay, don't look at the book first. Finish this one first, and then compare to the book. That's check. If you don't get the same one, then check what's the difference, or you can come ask me during office hour. All right. Okay, any question about this process we just went through? No? Yes?
The expression for the sum of the moments about A is a function of the reaction force at A.
So then you talk about this equation here. Equation of equilibrium?
The MA term at the bottom there. The reaction force at A is passing through A. Why does that have an effect on the sum of the moments about?
You talk about this equation. Oh, this equation here?
Yes.
Okay, where does this equation come from? It comes from here.
Right.
From here. Okay, where does this come from? From here. Equilibrium.
But we're taking the sum of the moments out, the sum of the moments out. Okay, I lost track. Sorry.
Okay. Well, maybe I didn't make it clear. But anyway, it's a moment about 1 point must be 0, independent equation. Right. Okay, any other questions or something unclear? All right. So we have a little bit of time, so I want pose a question for you is, let's say we use a different approach. Okay, let's say this beam, you can see here. What if I change this beam to this way? I'm not removing the moment here. I'm removing this RB as additional redundant restriction. How can you solve it with this? Right? The load still be the same. So you reduce the structure will be this one. Okay, so your reduced beam is actually a cantilever beam. Now how can you solve it? Use this approach instead of this picture, this approach. Yes?
Instead of saying that the angle is theta at that point of 0, you say that the derivation at that point of 0?
Yes. Short answer is yes. Okay. Anyone got it? What's the process? Okay. So you can do this way because you remove RB, right? So the equation of equilibrium still be the same, right? But you remove RB as a redundant. So therefore your structure becomes this one. Now when you write the equation about bending moment equation, right? So this will still be the same. Is this the same? This is the same, right? When you, because this equation is how you write the moment equation, that's still the same, right? Okay, now this will be the same. So this will be the same. So you will still have 1, 2, 3, 4 unknowns there, right? Okay, what will be different if you reduce the structure into this one, into this red one? So your equation will pretty much the same. Okay, what will be different? How can you make, let me ask, how can you make this beam deform the same way as this beam? Boundary.
What the difference is between the original beam and the red one now?
Okay. Okay, first, what's the difference between the blue one, original indeterminate beam, and this red one I'm just drawing? The difference is I remove the restriction here and replace it with replace with this RB, reaction force.
Is there RB in it?
RB I still don't know, but instead of restriction, I mean, right, reaction restriction there, I change it to a force. I treat it as a load. It's an unknown load, but it's a load. It's not a reaction anymore. I don't treat it as a restriction. I treat it as a load. Once I treat it as a load, now this becomes a determinate beam. So I can write the equation about it, and the equation will be like this here, the same. Right? And now I need the boundary condition or the compatibility to determine the constants. So that will be the next thing. Okay, so what will be the boundary condition that will make this beam the same as this beam? So you're going to have, we can write it here. So at v at x equals 0, v at v prime at x equals 0 because it's a cantilever beam, right? But also here v at x equals L equals what? Equals 0. Okay, then this beam will become the same as a beam there, right? So you have 3 conditions, boundary conditions you can use. Okay, so how can this one be compatible to the other one? Which equation of the 3 boundary conditions is actually the compatibility equation? It's this one, right? It's still the same 3 equation as you see here, but it's now this one make it compatible. Now it becomes this one make it compatible. It's all the same. It's just this one, right? If you don't distinguish them, you know, it's all the boundary conditions. It's still the same 3 boundary condition, but determinant constant. So when you solve it, it's not much. Concept-wise, you know, this in this one, this is the compatibility equation. In the other one is the other. Okay. All right. Any other questions? Okay, if not, try the homework. Okay, I'm going to give you homework again. So try one homework, and then next time we'll talk about using superposition and the table to solve it. You will see we don't need this process, right? Remember we talked about for determining beam, you don't have to do this process using superposition. Okay, if you can remember, try bring your textbook because we need to use the table at the back there. All right. Thank you. We have a few minutes. If any questions, you can just come over.
The tests are going to be graded by Monday.
Monday or Wednesday. I cannot guarantee Monday. Yeah, I'm trying to basically use this weekend to grade it. All right.